So in project risk management, you have probably heard at this point of EMV, or expected monetary value, and you probably heard of decision trees, which are used to map out different possible decisions that could be made that deal with uncertainty in terms of outcomes. So when you take an action, there's a result that occurs, and there's different results that can occur and different chances of those results occurring for different actions that you take. And you keep on mapping out the actions and the possible results and the likelihood of those results until you arrive at a net path, which means that you've ended that branch and there's an overall outcome that exists. And then you go back and calculate your values using the EMV formula, probability times impact, and you will arrive at the EMV value that provides the best outcome. So with projects, usually that means the lowest cost. For operations, it usually means the most amount of payoff. But operations and projects are very different. And as we know, projects do not make companies profit. They don't make the company money. They cause organizations to incur costs that can deliver something that will create profits in the organization down the road, but the project itself does not create a profit. So many of the models that you'll see in decision trees are using examples of operations that deliver a profit. But in project risk management, it's important to look at that in terms of the best EMV value is going to be something that is the lowest cost in most cases. So that is all good, but we have to understand that using decision trees in the way that's presented to us, for example, in the PMBOK, uses single point estimates. In other words, if we have an outcome that has a price that we pay, that's a single point. We estimate what that price would be. If we have an outcome that has a potential cost impact, such as a risk or a risk response has a certain cost impact, the cost is going to be a single estimate. So if we predict that a risk response plan might cost $10,000 because of previous projects that have had that same risk response in the past, and we use historical information to, and maybe some expert judgment to come to that conclusion, that doesn't take into account uncertainty. And there are some pieces of software where you can take that into consideration. You can use something called what-if analysis, which would take a range of variability, and that kind of gets to where we're going with going beyond single point estimates. So single point estimates can take the form of an average, or they can take the form of the median, which is the middle point within a range of data. So the middle number between the highest and lowest, or the mode, which is the most likely outcome, which is really what we're talking about when we look at single point estimates. The most likely outcome, the most likely value within a range of possibilities would be what most people select in projects. But with single point estimates, in projects, we want to look at this in terms of quantitative analysis. And what we do in project risk management is we take a 3-point estimate called the PERT estimate. And that is takes the range of possible outcomes. This is used when you have expert opinion to try to get the best guess for predicting risk impacts for projects. So it's called the PERT estimate. And what we end up with is lowest expected and highest value. So the lowest cost would be the best case, what we expect that project risk to cost an organization in terms of time or money, and then the highest, the worst case. Okay, but the issue with that is that we have all these values in between. Okay, so if we look at all of those values in between, at any given point, from the lowest to the highest, any possible outcome could exist. So anything in this range is possible. So if we're estimating project risk costs in terms of time or schedule-based costs, which are the most commonly used forms of costs, or what impact the project risk might have on the organization, it's very difficult to know what the answer is, what the actual risk is of a project when we have all these possible ranges. So to solve this problem, what we do is we use probability distributions. Okay, so using probability distributions, that can be done in terms of duration or time or cost or even resource requirements where there's some variability. Unless you believe in the world that everything is fixed and guaranteed, then you must believe that there are uncertain possibilities for the estimates that you use. You could be right or you could be wrong. And if you're wrong, you could be wrong within a range of values. And that is called a distribution. So different variables that you're using in your analysis and your estimates have different probabilities of occurring. So because of that, we use probability distributions. And in the PMBOK, most of the time, most of the examples use a normal distribution, otherwise known as a bell curve. What this basically is, the most common example would be people's heights. Okay, so if you were to take any given sample or room of people and measure their heights, you would find that it's most likely associated with a normal curve, meaning that it's just as likely for somebody to be taller than the average person in the room than it is for them to be shorter than the average person in the room. So people's heights are a good example of a normal distribution, and this is an example of a normal distribution. So at the top of the point, you'll see the mean value. The mean value, again, is the average value. It's not the same thing as the median or the mode. The mean is the average. If we added everything up and divided everything by the number of units we have within that sample, that's our mean. And you can see that the curve is symmetrical. So on the left and right side, if we were to plot, time against number of activations, for example, or costs on the x-axis and probability on the y-axis, okay, then we can see that the farther away we go from the mean on the right side, meaning that the higher the value is to the average, the less likely it becomes to the point where those tail ends are very close to almost no chance of occurring at all. And the same thing with the left side, which is lower than the average, but it's symmetrical. And there are many examples in life, and the best example is people's heights. That is not to say that all examples are that way. For example, weight. You might think that it is more likely, you have the same chance of being heavier than the average person than you do being lighter than the average person, but that would not be correct. Weights are not the same thing as heights. In fact, you have a higher chance of being heavier than the average person than you would be of being lighter than the average person, because you can essentially get as heavy as you want as a human being, but at a certain point, you cannot get as light as you want as a human being. So it's far more skewed to the right side of the mean than the left side of the mean, and that's a different type of distribution. In project management, we use a beta or PERT distribution, which is a 3-point distribution. It's a special kind of distribution. So there are two ways to discuss PERT. The first one is the distribution itself, meaning the values from the lowest or the most pessimistic if you're talking about cost, or the most pessimistic if you're talking about the lowest payoff in terms of a profit-based situation. But in either way, the lowest point is going to be the pessimistic and the highest point is going to be the most optimistic, or the best case scenario and the worst case scenario. And then what you expect, that distribution is any value within those ranges. Okay, so that's one way to talk about PERT. The other way to talk about PERT is calculating an average using a formula. So I'll show you that in a moment. This is a variation of the triangular distribution, which is literally just taking 3 points. So if you told me, if I asked you what do you believe the most pessimistic estimate would be for you to clean your house how many hours would it take you to clean your house? What would be the worst case scenario? Meaning, what would be an estimate that would take you the longest? So you might think, well, I've cleaned my house before, and it's maybe taken me 5 hours because I've been interrupted. I haven't really gone as put as much work in as I normally would, and as a result, I spent 5 hours. That's probably my worst job I could possibly do. And then I asked you, okay, well, what's the fastest you could do? Which would be the most optimistic, okay, the fastest, so the lowest value in this case. So you might say, well, if I really worked hard, I might be able to clean my house in maybe 2 hours. But if I really, really, really got sidetracked, pessimistic estimate would be 5 hours. Okay, well, then we have the most optimistic value would be the lowest value in this case of 2 hours, and the most pessimistic would be 5 hours. So then I would ask you, well, what do you expect it would be? What do you expect in terms of cleaning your house? In your experience, what do you expect that will be the most likely situation? And you might say, well, I could clean my house in 3 hours. That's usually what I do. All right, so then we just simply take those three values, 2 plus 3 plus 5, and divide by 3. And that gives us a triangular distribution. That's a simple average. However, the PERT average skews the value of the average closer to the expected value by using a formula, which I'll show you in a moment. But this is a variation of the triangular distribution. You can see on the left side we have the optimistic. So this is in terms of time. So in this case, 10 is the most optimistic, the least amount of time or the least cost. The most likely is probably somewhere around 13. You can see there the 15 is the average, that's called the PERT value. And then we have the most pessimistic down at 25, so that could be $25 or 25 hours or minutes or whatever it might be. Anything within that range is uncertain. We don't know what will actually be the outcome, but we know the lowest value is going to be the optimistic and the highest value, the pessimistic, and then that distribution approaches 0 on the tail ends. Okay, now the PERT value you see on that line on 15 is using the average, and you can see that it's very close to the most likely. Okay, so if we took a triangular distribution, that value would be higher than the PERT value, because the PERT value skews the average closer to the most likely value, because that, generally speaking, in projects, the most likely value is the closest value to reality. So we want to take into consideration the optimistic and pessimistic in our formula, but we're not going to use a simple 3-point estimate. We're going to use the PERT estimate. Okay, so remember, the mean is the average between the highest and lowest value in a range, also called the expected value. The mean in this case is going to be, let's say that we were measuring the heights of students in a room, in a classroom. So we might measure the height of student 1, who is 160 centimeters, student 2 is 170 centimeters, and student 3 might be 163 centimeters. So to calculate the average, we simply take the mean value of 160 plus 170 plus 163 and divide that by 3. And that's a simple average, known as the mean average, is 164.3 centimeters. So that would be our average value. And in many projects, project managers, we use the mean value. That is not the same thing as the mode, which is the value that is most likely. So the mean value is just the average value, and many project managers would use that value. Okay, but if we use a PERT estimate, we can see that there's a slight difference, a slight variation here. It's similar to the mean, but it's weighted more towards the expected value. And the PERT value, the formula is the optimistic plus 4 times the estimated value plus the pessimistic value, and divide all that by 6. So you can see there's a weight of 4 times the estimated value in this average. So now if we take the PERT value, our value goes to 163.6, which is 160 plus 4 times 163, assuming that our expected value is in the middle, and our pessimistic value is 170. So in this case, we're saying that taller people are pessimistic, not to discriminate against tall people. It's just in this particular example, that's the formula that we're going to use. And divide that by 6 is 163.6. And we can see, going back to our original triangular distribution, with a slightly higher average of 164.3. This is using PERT. So you can see that our average will drop. It'll be lower as we go more towards, we weight more towards the expected value. Okay, so that's using a PERT estimate, which is like a project management average that's used. It's a weighted average. Now, we have standard deviation, otherwise known as sigma. What is standard deviation? Well, quite simply, it's a measurement, a statistical measurement used to determine the range. It's used to determine the range of possible outcomes or the average distance between the mean value. In other words, it's used to calculate values, and it's used as a unit of measure to communicate how far away something is from the mean value. So as we go, in example of heights, taller or shorter than the average person in a room or an average person in a sample. So in project management, we calculate standard deviation using a 3-point estimate scenario. It's not the same thing as what you might have learned in statistics. It's a very simple formula. And the formula is the optimistic minus the pessimistic divided by 6. So optimistic is the best case scenario and pessimistic is the worst case scenario. So if we take our example again of our 3 students, we would say that the pessimistic is 160 and the optimistic is 170. So then we just take 170 minus 160 and divide that by 6. It's going to give us a standard deviation of 1.66 centimeters, meaning that the students that are taller than the average student would be taller by 1.66 centimeters, which is equivalent of 1 standard deviation from the average or the mean. And also students that are shorter than the average would be less than the average by 1.66 centimeters or 1 standard deviation from the mean. Okay, so keep that in mind. We have the PERT, we have standard deviation. Now we're going to discuss the confidence interval, which ties all of this together. Confidence interval is a measurement that's used to determine how far away a specific value deviates from the mean, represented by the standard deviation values. So here's a table that shows you how many standard deviations exist and the confidence level. So when we have 1 standard deviation, the confidence level, and that's plus or minus from the mean. So in other words, 1 standard deviation greater than and 1 standard deviation less than. So all of the range of values within a distribution, that would represent 68.26% of all of those values. If we went even further away from the average, in terms of 2 standard deviations, we can see that 95.46% of all values within that range fall within 2 standard deviations. So we are covering most of the values within a distribution. If we do 3 standard deviations plus or minus from the mean, it's 99.73. And you may have heard of 6 sigma before. 6 standard deviations from the mean is 99.99% of all of the input values between the distributions. So there's almost nothing, nobody in this case would be 6 standard deviations taller or shorter than the average student in any given classroom. Almost impossible that you would be that. So let's plot this using a normal distribution. This is going to be a little easier to understand. We can see that in the normal distribution, at the bottom on the x-axis, you see -3, -2, -1, 0, +1, +2, +3. Those are standard deviations. So they're like markers that we use to measure how many people or how many units of anything in a normal distribution are greater than or less than the mean. And we just use standard deviations as plot points so that we can graphically represent this, in this case, using a bell curve. So you can see in the middle is 0. Well, why is it 0? Because we have 0 standard deviations from the average. Everything is focusing on that middle value. That's the mean value. And you can see 34.13% of input values in this distribution are 1 standard deviation greater than the average, and 34.13% of input values in this distribution are less than the average by 1 standard deviation, which is on the left side. And it goes on and on and on. So in the middle, we would see, if we were using PERT values, we would see the PERT value in the middle, which is our average, is 163.6 centimeters, which we calculated earlier, meaning that the average student using PERT, let's say this was a project, the average height of a student in a classroom is 163.6 centimeters. Now, if we want to find out how many students, or the likelihood that students will be 1 standard deviation taller or 1 standard deviation lower or shorter than the average, we use our calculation of standard deviation, which we've calculated at 1.66 centimeters greater and 1.66 centimeters less than, which is 1 standard deviation from our average, 68%. So in other words, 68% of students will be between 162 centimeters and 165 centimeters in height, which is quite a lot of students in the class. Now, we could do that for all standard deviations. Let's look at the 3rd standard deviation. Okay, that means we're almost 5 centimeters taller and 5 centimeters shorter than students the students that are at the average height of 163 centimeters, meaning that 98% of the students will fall between 158 centimeters and 168 centimeters tall. Anyone that is taller than 168 centimeters or shorter than 158 centimeters, okay, that would represent about 2% of the students in the class. So it's a very small amount, if that. Okay, so this is what we mean by confidence intervals. And a confidence interval, why do we care about this? Why are we talking about this for project management? It's because, again, the issue with single point estimates and this issue, what happens if we are using single point estimates and anything within the range is possible? Why are we talking about confidence levels? Well, we talk about confidence levels because we want to use a stochastic model or a probability distribution model, a probabilistic model, when answering the question of what risk values are associated with those project risks and how risky is the overall project. We want to be able to use a stochastic model instead of expressing the risk with certainty in terms of a single point estimate. So if we use this model, this calculation still is a single point estimate. It still will give us one number, and the number here is 163.6 centimeters. So if you told me that, if I asked you what the height of a student will be in a classroom, okay, it's very easy to answer that and say, well, the average would be 163 centimeters using PERT, and you would be correct by saying that. But it is still a single point estimate. And when we are using PERT to calculate and to estimate project risks, we are taking into consideration a range, but we're still using the single point estimate. It does not take into consideration this issue of anything that could exist within that range. So we have to answer the question differently. Instead of answering the question in terms of a number when asked, how risky is that event? How much exposure is the project facing in terms of the cost of that risk, or the impact of that risk, or how risky is a project? Instead of answering that by giving a number, we need to start learning to answer that question in terms of a confidence level. And the confidence level is determined by the sponsor, the organization's appetite towards risk, the amount of aversion that they might have towards risk. The culture of the organization will determine that, so that we can answer the question in terms of a confidence level, and then from the confidence level, we can determine the corresponding value. So for example, if our project, we were willing to accept a value of confidence of 68%, then we know what we need to consider is any range between 162 and 165 in this case. 68% of all inputs will be between that range. However, if we want, that doesn't take into consideration all of the other possibilities to the left of that red square and to the right of that red square, greater than or less than. So if we're an organization that doesn't want to bear much risk, so we need to make sure that we are considering a far greater amount, perhaps we have very little appetite for risk and we cannot bear that level of risk. We need to make sure that we are covering more variability. For example, 98% confidence. We know that we therefore need to cover a greater range. 158 to 168 would be as an example of that. And we do this through Monte Carlo simulation. Monte Carlo simulation takes into consideration the distributions that you decide to use, which are single point estimates. But unlike single point estimates, which just use formulas and give you a single number of any kind, typically what you will have is project managers who take, Excel models or mathematical formulas, linear equations, we'll say, and they'll plug in different values for the inputs. For example, for risks, they might change some of the numbers and enter pessimistic and enter optimistic values. And from there, they can look at something called what-if analysis and gauge how much the project is impacted if the units change. Okay, and that's an exercise that's worthy of discussion. But Monte Carlo simulation is far more advanced, and what it does is it takes those values and simulates the project along the distribution that you assign. And as it simulates the project, it adds up, it accumulates all of these values into a model. And then after running the model, and it can be sometimes hundreds or thousands or even millions of times, it assigns random values along this distribution. So any given point, at the lowest point or the highest point, and anything in between, for all of your risks, for all of your inputs, for all of your activities, whatever your model is going to be associated with, it will take into consideration any one of those values, and it will calculate the averages. It calculates a variety of different statistical measures, and it will give you something called a S-curve, histogram, tornado diagram, sensitivity analysis, many different features of Monte Carlo simulation, which can be interpreted. So Monte Carlo simulation, according to PMBOK, it simulates the combined effects of individual project risks and other sources of uncertainty to evaluate their potential impact on achieving project objectives. It's using sophisticated computer analysis, and it takes multiple versions of possible realities, usually thousands or even millions of different times, and it determines the likelihood of reaching a given result. You decide what that is. Okay, so questions that you can ask using simulation are, what are the odds that we'll stay in budget? Okay, so we have our baseline budget. What's the average? What's the odds that we're going to stay on that budget? How likely are we to stay within our schedule? How risky is the project? How much money should we set aside for a contingency reserve? Some outputs that you'll have is a histogram, which is basically just a bar chart, and an S-curve, which is shown from the PMBOK right here. And an S-curve, in this case, it's cumulative, and it's easy to interpret this. In this case, we're looking at a cost-based S-curve. So we have on the x-axis cost, On the y-axis, probability. And this is cumulatively adding up all of the different project simulation results, whether it's hundreds or thousands or millions of times, and it calculates the probability of reaching certain costs based on what the results were. So for example, if we look at along the x-axis $41 million, and then we find the corresponding probability, that tells us that 12% of the projects using the model and Monte Carlo simulation, 12% of the projects cost $41 million. However, the remaining projects results cost more. So we know, we can safely say our confidence level would be 12% that the project will cost $41 million or less. So that is probably not going to be acceptable for most stakeholders, for most sponsors who want to have more confidence. So another way of looking at this might be that you can see the mean value at $46.67 million. Suppose that we used an average. We talked to some experts and we did 3-point estimates. And we looked at the optimistic, pessimistic, and most likely values. And we determined through that formula that the average was $46.67 million. And that became, for example, what we estimated the project would cost using a simple PERT estimate. Now, remember, that's still a single point estimate. It does not take into consideration the uncertainty within a distribution. So if we use the stochastic method, which is used in Monte Carlo simulation, we can test that value using our S-curve to determine how confident we actually are that we have arrived at the right number. And we can see if you follow the chart at $46.67 million, follow the line up the S-curve, you will see it intersects the S-curve at 50% probability. 50% probability means that we are 50% confident that our project will cost $46.67 million or less. But there's still a 50% chance that the project will cost more than $46.7 million. So then the question becomes, a discussion has to occur, which is the organization willing to accept a confidence level of 50% based on our original PERT estimate of $46.67 million? Using stochastic analysis, using a stochastic model, and looking at probability distributions, if the organization determines that they will not accept projects that they can't be at least 75% confident they will have enough of a contingency to cover those costs, then we can simply look at our model and determine what that value would be. So you can see at 75%, follow the line to the S-curve, and that corresponding cost is $50 million. So if we need to have $50 million in reserves to be able to cover the 75% confidence level, and if that's something that the organization accepts, it means that our original estimate of $46.67 million for our budget will not be enough. In fact, we're only 50% confident that that will be enough. If we want to be 75% confident, we have to increase that value to $50 million, or we have to add the difference between 50 million and 46.67 into our contingency, so that we can therefore meet the requirements of the stakeholder or the sponsor or the organization in terms of their confidence level. So this is what Monte Carlo simulation does and allows for the organization to do. The other thing a Monte Carlo simulation allows to do in its outputs is something called a tornado diagram, which project managers call sensitivity analysis. And this breaks down individual risks in terms of how much they impact the overall project. And the best way to describe this is simply looking at the individual risks and determining using scatter diagrams or regression analysis, as those values change, is the project cost changing with it? And if the total cost of the project is not changing with those values, it means that the project is not very sensitive to those risks. But some risks are, they cause a lot of variability with the project, and that means the project is very sensitive to those risks. So it's a tool for simulation results used to address the potential positive and negative impact on the project objectives for each risk. It's useful when determining which risks should be pursued given the variability in outcome. So that's going to be useful for you after looking at your model to examine those risks and maybe prioritize them and investigate them further versus the risks which don't appear to cause a lot of variability in the overall project. Here's an example, and we can see on the line there, which divides the risks. We have 6 risks. On the line, we have the average. Okay, so that would be the average cost of the project. And you can see to the left of that line, there is a grayed out value, and to the right of that line, there's a black value. And you can see that there are negative numbers and positive numbers. The negative numbers represent the values being less than the average cost of the project. The numbers on the right side of the line represent the values where the project was over the average. So we have risk 1, 2, 3, 4, 5, and 6, and this is called the tornado diagram because by default, the output values are lined up from the risk which is the project is most sensitive to at the top, all the way to the bottom, which represents risks that are the project is least sensitive to. So risk number 1, we can see that when the risk is at its lowest value, which is nearing 10 at its lowest value, and on the left side of the line, the project risk is the overall cost of the project is impacted by almost $10,000 less than the average. Whereas when the risk is at its worst, at its highest point, the project is impacted by about $18,000 or so. So this risk is causing a lot of variability in the overall project cost versus all the way down to risk number 6. Well, as that risk changes at its lowest and highest point, the project is hardly changing at all. So that risk is having very little impact on the overall cost of the project. So in other words, when risk 1 does occur, and when it does occur, as it impacts the project overall cost is significantly impacted by risk 1. Whereas if risk 6 does occur, and if it does occur, the magnitude of the impact on the project has very little effect on the overall outcome of the project. And if we work our way up from risk 6 to risk 1, we can see that these risks they have varying degrees of positive and negative impacts on the overall project risk. So when you're interpreting a tornado diagram, look at the top risk first and work your way down, and it helps you to better understand how the risks are impacting the overall risk of the project. So using sensitivity analysis, it takes the range of the overall risk impact value for each project, but project risk. But this diagram is plotting the overall cost of the project risk, independent from all of the other risks. So it's used independently. Risk 1, 2, 3, 4, 5, and 6 are being analyzed independent of each other. So it really helps you to form a picture of the risks that are causing the most variability in the overall project versus the ones that are causing the least amount of variability from a positive and negative perspective. Okay, so that's an example of looking at quite a lot of different things, starting with looking at probability distributions, going beyond single point estimates, and then we looked at the example of the PERT formula. We looked at probability distributions and something called standard deviation. The mean, which is in project management, is called the average, but it's using the PERT formula and calculating the PERT formula and standard deviation. We looked at a normal distribution, and we looked at the PERT distribution, which is not the same thing as the formula. A PERT distribution is a range of possible outcomes within a 3-point estimate. Okay, and then we looked at using confidence intervals, which take into consideration the standard deviation from the average, in order to then transition to Monte Carlo simulation, which is a stochastic or probabilistic approach to quantitative risk analysis. And that is very powerful in terms of some of the outcomes. The main 3 that are used in project management would be histograms, which is a bar chart, which you'll see in in risk management software as an outcome, a very popular outcome. The S-curve, which we looked at, and then the tornado diagram, which was used in sensitivity analysis. I hope you enjoyed this video and got something out of it and learned something about the project risk management quantitative methods, in particular, looking at risk management beyond single point estimates, looking at risks and how they impact projects beyond using single point estimates, and instead using probabilistic methods for better analysis.